Weathering and landslides, how mountains crumble and hillsides fall. Every mountain we admire is a masterpiece in slow motion, built over millions of years by tectonic fury, and then unbuilt, grain by grain, by the quiet forces of weathering and gravity. Rock shatters. Minerals dissolve. Slopes creep, crack, and, sometimes with terrifying speed, collapse. Today, we'll journey from the bedrock under Ibadan's Mapo Hill to California's Big Sur coast, from Yosemite's exfoliating domes to Italy's catastrophic Vajont landslide, from the chemistry that turns granite into clay to the rainfall thresholds that tip hillsides into deadly debris flows. By the end, you'll see how landscapes evolve, why landslides happen, and what we can do to live safer on a dynamic planet. Part 1. Weathering, the art of taking mountains apart. Weathering is the suite of processes that break down rock at or near Earth's surface. It happens everywhere, whether on a wind-scoured ridge, a tropical hillside, or the stone beneath your feet. Think of weathering as nature's toolbox: mechanical, physical weathering that breaks rock into pieces, chemical weathering that alters minerals into new substances, and biological weathering driven by roots, microbes, and burrowing creatures. Weathering weakens, cracks, peels, dissolves, and stains. Then erosion, by water, wind, ice, and gravity, carries the fragments away. Together, weathering and erosion sculpt the landscapes of the world. Mechanical, physical, weathering. Mechanical weathering breaks rock without changing its chemistry. Frost wedging pries open joints as water freezes and expands. Salt crystals grow in pores and push grains apart in arid coasts. And in massive granites, sheeting, or exfoliation peels off slabs parallel to the surface as overlying pressure is released. One reason domes like those in Yosemite acquire rounded, onion skin forms and occasionally shed huge rock sheets as rockfalls. Chemical weathering. Chemical weathering transforms primary minerals into secondary ones. A classic example is hydrolysis. Feldspar in granite reacts with acidic water to form clay minerals such as kaolinite, releasing ions like potassium, silica, and bicarbonate into groundwater and streams. It's why fresh granite looks bright and speckled, while weathered granite can feel chalky and friable. The feldspar has literally become clay. Over deep time, such alteration produces thick, reddish lateritic profiles in the tropics. Biological weathering. Life accelerates both mechanical and chemical weathering. Plant roots wedge into fractures, microbes and lichens secrete acids, burrowing animals churn soils. On humid tropical bedrock, intense biological activity can speed the conversion of crystalline rock into saprolite, a crumbly, clay-rich residuum that still preserves the original rock's texture but has very different strength and permeability. In southwestern Nigeria's Precambrian basement complex, studies of weathering profiles show common secondary minerals such as kaolinite, goethite, and limonite, evidence of vigorous chemical weathering in warm, wet climates. A Nigerian example, Mapo Hill, Ibadan. If you've ever climbed the steps to Mapo Hall, you've stood on a weathered inselberg, hard, resistant basement rocks that rise above a lowered landscape. Across southwestern Nigeria, granite gneiss terrains and their inselbergs trace a long history of deep weathering and stripping. The bedrock here is part of the Pan-African Mobile Belt, and the soils and saprolites developed upon it record the chemistry of rock breakdown in humid tropics. Part 2. What weathering leaves behind. Weathering doesn't just weaken rock, it creates materials and landforms. Mechanical weathering builds talus cones and exfoliation slabs. Chemical weathering yields clay-rich horizons, bouldery corstons, and thick regolith mantles. In Nigeria's basement terrains, geophysical and geochemical studies document deep saprolite from intense weathering, overlain by soils whose mineralogy reflects that bedrock transition: quartz as a survivor, kaolinite as a product, iron oxides as stains. This matters because weathered profiles control hydrology, how water moves, land use, foundation strength, agriculture, and slope stability, how likely a hillside is to fail. Clay minerals can reduce permeability, trap water, and weaken slopes after heavy rain. Fractures and joints guide both root growth and future landslides. In short, weathering sets the stage, gravity writes the drama. Part 3. Mass movement, when gravity takes over. When rock and soil move downslope under gravity, geologists call it mass movement or mass wasting, and landslide is the umbrella term. The U.S. Geological Survey classifies 5 primary movement types: falls, topples, slides, spreads, and flows. Material can be rock, debris, or earth. Water content and speed vary from imperceptible creep to roaring debris flows. Creep, millimeters to centimeters per year, tilting fences, bent trees. Rockfall, topple, blocks detach and free fall or pivot, common on jointed cliffs. Slides, coherent masses slip along a plane, rotational or translational. Debris, earth flows, water-saturated mixtures surge like wet concrete, fast, dangerous. Lateral spreads, ground breaks apart on gentle slopes, often in sensitive clays or liquefied soils. Part 4. Case studies, from California to Italy, and lessons for everyone. Post-fire debris flows, Montecito, California, 2018. In January 2018, intense rain fell on steep, fire-scarred slopes above Montecito, California, triggering high-speed debris flows that swept through neighborhoods, killing 23 people and destroying hundreds of homes. In burned terrain, only 0.3 inches, approximately equals 7 millimeters, in 30 minutes has triggered debris flows. The Montecito storm delivered extreme short-duration intensities, well above common design thresholds, after the massive Thomas fire removed vegetation and water-repellent ash-mantled hillsides. The deadly mix, steep catchments, loose sediment, and short-burst rainfall exceeding intensity duration thresholds. Highway 1, Big Sur, Mud Creek, 2017. Along California's Big Sur coast, the Mud Creek landslide catastrophically failed in May 2017, burying roughly a quarter mile, approximately equals 400 meters, of Highway 1 under greater than 20 meters, approximately equals 65 feet, of debris and even adding new coastline. The event followed an exceptionally wet winter that saturated coastal slopes. Oso, Washington, 2014. In March 2014, a hillside near Oso, Washington collapsed across the North Fork Stillaguamish River, devastating a community and killing 43 people. The slide mobilized rapidly, partly due to saturated glacial sediments and prior slope instability, illustrating how rainfall, weak stratigraphy, and legacy landslides can combine into a catastrophic failure. Vajont, Italy, 1963. One of history's most sobering slope disasters wasn't a natural hillside alone, but a human-made reservoir beside an unstable mountain. On the 9th of October 1963, around 260 million cubic meters of rock from Monte Toc thundered into the Vajont Reservoir in northern Italy. The displacement wave overtopped the dam by approximately 150 to 200 meters, obliterating towns below and killing roughly 1,900 to 2,000 people, while the dam itself remained standing. The lesson: slope geology and water levels can interact catastrophically, even without a dam failure. Part 5. Weather, climate and AMP, the landslide connection. Rain is the most common short-term trigger for landslides. Intensity matters more than total accumulation. High rainfall rates in 5 to 30 minutes are often the critical push for post-fire debris flows. Field monitoring in Southern California shows debris flow initiation correlates strongly with 15-minute intensity, I-15, during the first rainy seasons after wildfire, when vegetation hasn't recovered and soils repel water. Zooming out, a warming climate is changing precipitation patterns. In many mountain regions, heavy precipitation events are increasing, compounding landslide risks alongside glacier retreat, thawing permafrost, and more frequent rain on snow events. The IPCC assesses increased hazards such as floods and landslides in mountains as temperatures rise, with regional detail showing heightened risks where extremes intensify. Part 6. How slopes fail, triggers and AMP conditions. A slope fails when driving forces, gravity, water pressure, vibration, exceed resisting forces, rock, soil strength, friction, cohesion. Key factors include water and pore pressure. After storms or snowmelt, water raises pore water pressure, reducing effective stress and friction. In saprolite or clay-rich layers, this can lower shear strength dramatically. Geology and structure. Weak layers, clays, volcanic ash, unfavorable bedding, weathered joints, and ancient landslide deposits predispose failure. Erosion. Streams or waves undercut slopes, gullying steepens hillsides. Earthquakes and vibration. Seismic shaking can trigger rockfalls and slides. Even construction vibration destabilizes sensitive slopes. Human activity. Road cuts, deforestation, leaking pipes, and poorly managed drainage concentrate water and remove root reinforcement. Fire. Post-fire slopes are especially hazardous. Ash layers repel water, roots are gone, rainfall thresholds drop to strikingly low values. Remember, weathering prepares, water triggers, gravity delivers. A deeply weathered mantle supplies the weak material. A storm supplies pore pressure, and gravity completes the process. Part 7. Types of landslides, with real-world texture. Let's anchor each type with a mental picture. Rockfall, topple, a cracked granite wall in a hot, cold climate, shedding slabs along sheeting joints. Yosemite is textbook, with exfoliation producing giant plates that ultimately fall. Rotational slide, a curved failure surface, trees tilting backward on the slump block, hummocky toes, common in clay-rich hills. Translational slide, a slab gliding on a weak plane, e.g., bedding, clay seam. Debris flow, mud flow, a thick, boulder-laden slurry racing down a channel. Montecito is the cautionary emblem. Post-fire thresholds are low. Lateral spread, gentle slopes breaking apart over liquefied layers during earthquakes. Creep, fences bowed, tree trunks J-shaped, slow yet relentless. Part 8. Prevention, mitigation and AMP, early warning. We can't stop weathering, and we can't turn gravity off, but we can manage risk. Here's how communities, engineers, and residents reduce landslide hazards. 1. Drainage is king. Divert surface water away from steep slopes. Maintain culverts and ditches. Install subsurface drains or horizontal drains to lower pore pressure. Line channels to prevent infiltration. 2. Vegetation and bioengineering. Preserve or restore deep-rooted plants to anchor soil and enhance evapotranspiration. After wildfire, prioritize erosion control treatments, mulch, wattles, before the first heavy rains. 3. Slope geometry and reinforcement. Regrade over steepened cuts. Build retaining structures, soil nails, rock bolts, and shotcrete where appropriate. Install debris basins in alluvial fan mouths to catch flows before neighborhoods. 4. Setbacks and zoning. Avoid building on historic landslide deposits, fan aprons, or below unstable scarps. Use hazard maps. Respect no-build buffers near channel mouths prone to debris flows. 5. Monitoring and early warning. Deploy rain gauges and intensity duration thresholds, like I-15, for automated alerts in burn scars. Use tilt meters, crack meters, and infrasound, seismic networks to detect moving masses. Integrate nowcasting and local thresholds for evacuations. 6. Good practice at home. Fix leaks. Route roof drains to safe outlets. Don't dump yard waste on slopes. Terrace appropriately. Plant wisely. Watch for warning signs, new cracks, sticking doors, bulging ground, tilting trees. Mitigation is a layered defense. Keep water out, keep roots in, keep loads light, and listen to the hills with senses and trained eyes. Part 9. Weathering processes, summarized, with take-home examples. Mechanical weathering, exfoliation, Yosemite domes, thermal stress, frost, salt, creates blocks and slabs that can later fall. Chemical weathering, Hydrolysis turns feldspar into kaolinite and other clays, oxidation rusts iron, dissolution carves limestones. These reactions build thick regolith in humid climates. Biological weathering, roots pry, microbes etch, termites and worms churn, accelerating the path from rock to soil. In Nigeria's basement terrains, lateritic weathering is well documented. From Mapo Hill to Igbajo's Inselbergs, from California's post-fire canyons to Italy's alpine valleys, the common thread is simple: weathering sets up the weakness, water tips the balance, gravity delivers the change. Part 10. Final word: living with a restless earth. Mountains rise and mountains fall. On human timescales, we mostly witness the falling, cracks widening after the rainy season, slopes slumping after storms, rivers hauling away the pieces. That's not a failure of the land, it's the normal life cycle of landscapes. So, learn your ground. Respect rainfall thresholds. Keep the water off the slope. Plant deep. Watch the signs. And support science-based planning where you live. If this deep dive helped you see Earth with new eyes, please like the video, share it with someone curious, and subscribe to Uncovering Facts for more crisp science storytelling every week. Have a weathering or landslide story from your area, maybe even from Mapo Hill or the Big Sur coast. Drop it in the comments. Your local observations could save a life.